Welcome back everybody. I am a teacher from Ilm Online Academy. In today's video, the topic is extraction and corrosion of metals. This is basically chapter number 16 of the ongoing series for the Cambridge Chemistry 0620, and in today's video we'll be having a look at this chapter, which is about extraction and the corrosion of metals. Without further ado, let's just begin, and I will tell you about the contents which we will discuss in today's video. So the contents which are included in this chapter are: first, the metal extraction and the reactivity series, and the second is the corrosion of metals. These are the two main important contents which we will discuss today. So first, if we talk about the metal extraction and the reactivity series. So most of the metals exist in our earth crust, and some metal exist as a pure state in the nature. Like we have so many examples of the pure metals that exist in the pure state, and we also call it as the native metals. For example, we have gold, we have silver. These metals exist as a native form, or we can say these exist as in the pure form, so we don't need to extract them from any other things. But some metals are difficult to extract from their compounds which are present in their ores. Some are present in their ores, and ores are a naturally occurring mineral from which a metal can be extracted. So this is ore. So most of the metals are present in the form of the ore, so we have to extract them from their ores. And those metals that do not occur in uncombined form in the ground, that are known as the native, and can be found as the metal and metal oxide, or the compound that can be easily converted to the oxide. So to extract the metal from the oxide, we need to carry out some reactions. Like some metal exist as so for example, we have a metal plus oxygen is attached to them, so it forms the metal oxide that is present there. So this is about the metals and the ores, native form, and the ores that are present in the earth crust. So next, in the previous chapter, in chapter number 15, we established that there is a reactivity series based upon the differences in the reactivity of the various metals. We read about that reactivity series, and we have placed the most reactive metals are those that combine more strongly in their compounds or form the positive ions more easily. And we also placed the hydrogen in that reactivity series because it is useful to know the reactivity relative to the different metals. And we also found out that hydrogen is less reactive than the zinc and more reactive than the copper. I will show you the reactivity series now for this one. So this is the reactivity series, and you can see here hydrogen is present below the lead and upper antimony, bismuth, and copper. So we place the hydrogen in this reactivity series because it's useful to know its relative reactivity to the different metals. We found out that hydrogen is less reactive than the zinc, as zinc is present there, and hydrogen is more reactive than the copper. As you can see here, copper is present below the hydrogen. So for instance, hydrogen will remove oxygen from the copper oxide to copper metal, but hydrogen will not reduce the zinc oxide to the zinc metal. Why? Because of its reactivity. As zinc is more reactive as compared to the hydrogen, so hydrogen cannot replace the oxygen in the zinc, but hydrogen can replace or can take the oxygen from the copper because copper is less reactive than that. And at the end of chapter number 15, we also comment that it is useful to place a carbon also in the reactivity series, and carbon is present below the aluminium and above the zinc in our reactivity series. Like we have carbon here. For example, if you have potassium, sodium, we have calcium, magnesium, aluminum, and here is the carbon that is present. Carbon is present below the aluminium and carbon is present above the zinc, so that means the metals that are present above the carbon are more reactive than the carbon, and the metals that are present below the carbon, that means those are less reactive than the carbon. So we can easily reduce any metal by the process of reduction by using carbon. Means that carbon can be used to replace the metals from their ores like zinc, iron, silver and gold, but not potassium, sodium, calcium and magnesium, and also the aluminum. Why not? Just because of that potassium, sodium, calcium, magnesium and aluminum are more reactive than the carbon, and this is the carbon that is placed between the aluminum and the zinc in our reactivity series. So metals that are present below the carbon can be extracted. These can be extracted by heating their oxides with the carbon, but those that are present above the carbon must be extracted by electrolysis. These can be extracted by electrolysis, and they cannot be extracted by using the carbon or by heating the oxides with the carbon, because they are more reactive. So if a metal is below the carbon in the reactivity series, oxygen in its oxide will form the covalent bond more easily with the carbon rather than remain as the oxide ion. So carbon is the reducing agent. Carbon here is used as a reducing agent. We can use, or we can do the process of reduction here, and carbon act as a reducing agent, removing the oxygen from the oxide. Like for example, we have zinc oxide. So this is the oxide. What will happen? Carbon will take the oxygen from the zinc oxide and will remain, we have the metal, that is the zinc, that is present there. So if the metal is more reactive than the carbon, then reduction must be achieved by the reaction that take place at the cathode during the electrolysis. The metal ions in the oxide must gain electrons to produce a free metal. This is the type of reaction that take place in the electrolytic extraction of the aluminum. We have also read about the electrolysis in the chapter number 6 in detail, and just to tell you in simple, electrolysis is the breakdown of an ionic compound or molten in aqueous solution by the use of electricity. Electro and lysis, there are two words. Lysis means breakdown, and we have electro, that means by the use of electricity. So these are the two words that form the electrolysis. So generally, the breakdown of an ionic compound, molten or aqueous solution by the use of electricity, that is known as electrolysis. So we have to do the electrolysis for the extraction of the reactive metals like potassium, sodium, calcium, magnesium and aluminum. So this is the introduction related to the extraction of the metals and the reactivity series. Next we will talk about the extraction of the specific metal. We'll talk about extraction of some metals in this chapter in detail. So first is extraction of the iron from the ore. We have the ores of the iron that are present in the earth's crust, and we will take that ore to extract the iron from its ore, because these are the reactive metals, right? So they can easily react with anything that is present below the earth crust, like oxygen, sulfur, any other impurity that is present there. Because of its reactivity, they will react, and they are in the form of the ore. Ore is the naturally occurring mineral from which a metal is extracted. So now first we will extract the iron from the ore. Iron is the second most common metal in the earth crust, and the main ore of the iron is the hematite, that is Fe2, that has the formula of Fe2O3, that is hematite. This ore of iron is known as hematite, which has the formula Fe2O3. So carbon is not highly reactive, but it's moderate reactive metal, and it's the second most common metal that is present in the earth crust. So we have so many uses of the we have so many uses of the iron. So we will use the iron in the maintenance, in construction, in bridges, in so many things. So for that purpose, we extract the iron from the earth crust. The main ore of the iron is hematite, that is Fe2O3. This ore is rich in iron that contain almost more than 60% of iron. So more than 60% of iron is present in this ore of iron, which is hematite. it is the major ore of iron, that is iron oxide, and we will do the production of the iron in the blast furnace, or the extraction of the iron from the ore. So this process of the extraction of iron from the ore will occur in the blast furnace. We have a blast furnace, and I will also show you the blast furnace, which is a tower that is made up of steel, and in that high temperature is provided for the extraction of the specific metal. So this process using the following things, like the first one, we should use carbon in the form of coke. Carbon in the form of coke is used. And that is made by heating the coal. Coke is made generally by heating the coal. And next we have a lime. So coke is made by heating the coal. And next thing that we require is limestone. The formula of limestone is CaCO3, which is also known as calcium carbonate. So we require, or we use these following things: first, carbon in the form of coke; second, limestone; and third, we require the hematite ore. This is the third thing that we require. Hematite is the ore of the iron, that is Fe2O3. So now I will show you here the blast furnace that is being used to extract the iron from the hematite ore of the iron, and that blast furnace is used for extracting the metals, particularly iron, by the reduction with the carbon that uses hot air blasted at the base of the furnace to raise the temperature. And we have a blast furnace that is made up of steel. You can see here, this is the blast furnace tower that is used for the reduction of iron ore to the iron, and this tower is 30 meters high. It is lined with the heat resistant bricks of magnesium oxide, which are present here. In the walls of the blast furnace we have bricks of the magnesium oxide that are present there, and they are heat resistant. And blast furnace is loaded with the raw materials. These are the raw materials that are required: hematite ore of the iron, and calcium carbonate, limestone, and third, we require carbon in the form of coke. So first, blast furnace is loaded with the raw materials, and raw materials will put here in this. And limestone is just a mineral form of the calcium carbonate. So what will happen next, the charge is centered and the ore is powdered and heated with the coke and limestone to make sure the solids mix well. You can see here, these are the powdered form of all these things, the powder one. So this forms here, and the charge is centered, the ore is powdered and heated with the coke and the limestone to make sure the solids mix well, and it is mixed with the more coke. So next, the blast of the hot air are sent to the furnace through the holes near the bottom. You can see here, these are the holes that are present there. Hot airs are sent into the furnace through the hole near the bottom of the furnace, and these two holes are there. And next, what will happen, we have series of chemical reactions that take place within the furnace to produce the molten iron. The first reaction of this one, so you can see here, this is the blast furnace, and here are a lot of chemical reactions, a series of chemical reactions that take place within the furnace to produce molten iron. The first reaction that happens in this furnace is the carbon in the form of coke that reacts with the oxygen, and it forms carbon dioxide. The carbon coke burns in the air blast, and the furnace gets very hot from this exothermic reaction. This is the exothermic reaction. Exothermic means a lot of heat is released when this reaction happens, because we know that exothermic reactions are those which releases heat. As the carbon dioxide rises, So when carbon dioxide form, it rises like this one. You can see here CO2 rises above through the furnace. It reacts with more carbon and it is reduced to carbon monoxide. So we have carbon dioxide from the first equation. When it rises to the top, it reacts with the more carbon that is present in the form of coke, and then it will form carbon monoxide like this. The most important reaction that then occurs is the reduction of the ore by the carbon monoxide. So carbon monoxide is here for the reduction of the ore. We have iron oxide or iron ore that is present in the form of hematite, and that iron ore reacts with carbon monoxide, and this is the reduction of the ore in the presence of carbon monoxide. So when these two react together, they form iron as a solid metal, pure metal as, plus we have carbon dioxide that is released. So these are the series of chemical reactions that take place in the blast furnace. First, we have a carbon or coke that reacts with the blast of hot air that comes in the blast furnace, and then carbon dioxide is formed. Carbon dioxide reacts with more carbon or coke and forms carbon monoxide, and then carbon monoxide reacts with the iron oxide to form this pure iron plus carbon dioxide. So this is how the reduction of the iron ore happens. The iron produced flows to the bottom of the furnace. Here you can see this one. This is the area from which molten iron is collected. Just because of that, the temperature is much higher in the blast furnace. That's why iron is in the molten form, means iron is turned from solid into the liquid state. So we get the molten iron, and after cooling it we have the solid iron. Next, as where it can be tapped off as a liquid because the temperature at the bottom of furnace is higher than the melting point of the iron. That's why we get the iron in the liquid form. We have some major impurities that are also produced in the iron ore, that is sand, or you can say that silica or silicon dioxide. We have some impurities that are also produced in this reaction, so you can call it as silica or sand or silicon dioxide that has the formula SiO2. So the limestone is added to the furnace, which helps to remove this impurity. So for the removal of this impurity, we are adding the limestone, which is calcium carbonate. So calcium carbonate undergo thermal decomposition reaction. So when CaCO3 is heated, it forms calcium oxide, CaO plus carbon dioxide is released. So carbon dioxide is then reacted with the more carbon. This equation you can see here, and then it forms the carbon monoxide. But calcium oxide, here you can see this, the lime that is produced here, calcium oxide or quicklime produced, then reacts with the silica to form the calcium silicate slag, like CaO plus silicon dioxide reacts, and then they form calcium silicate like this. So this calcium silicate is known as molten slag, and the lime is produced, or lime reacts with this just for the removing of the impurities from the blast furnace. So we have a molten slag. This is known as molten slag because of high temperature in the blast furnace. So all the things that are produced there in the molten form, and then you can cool it for converting into the solid form after removing from the blast furnace. We have molten slag. This is a molten mixture of the impurities, mainly calcium silicate, that is formed in the blast furnace. So the calcium silicate formed is also molten. It flows down the furnace and forms a molten layer of slag on the top of the iron. It does not mix with the iron, and because it is less dense, and the molten slag is tapped off separately. When solidified, slag is used for the concrete for buildings and also for road surfacing. This is an impurity for this process, but it has some other uses. For example, like for concrete for buildings and for road surfacing. The hot waste gases escape from the, you can see this one, the hot waste gases are removed or escape from the top of the furnace. The gases are used in the heat exchangers to transfer heat to the incoming air, and this helps to reduce the energy cost of this process also. So the extraction of iron is a continuous process. We are continuously adding the raw materials to this, and hot air or blast of hot air will move upward and forms carbon dioxide. So that's why it's a cheaper process than the electrolytic process and can be used to extract some metals. So next we will summarize all this extraction process. So there are some key features of the blast furnace for the extraction of the iron from the iron ore, that is hematite. In this we have, first of all, we have the burning of the carbon. So burning of coke or burning of carbon. And why we are doing this? We are doing this process to provide the heat. For the purpose of heat, as this reaction is highly exothermic, so that's why this is done to provide enough heat and also to produce carbon dioxide. For the production of the carbon dioxide and to provide enough heat for the reaction to happen in the blast furnace, so we do the burning of the carbon or coke. The second is the reduction of carbon dioxide. Reduction, that means reduce. So reduction of carbon dioxide to carbon monoxide, because carbon monoxide reacts with the iron ore or hematite. The third step is reduction of iron oxide by carbon monoxide. Reduction of ore by carbon monoxide. And this is the third important feature. And next is the thermal decomposition of calcium carbonate. We have the thermal decomposition of calcium carbonate to produce a quicklime. For the production of the quicklime, CaO and carbon dioxide is also released. So the quicklime is used to remove the impurities that are produced in this, and that impurity is the slag that is formed. Molten slag is there. So we use the quicklime here for the purpose of removing the impurities. Calcium oxide or quicklime reacts with the sand or silica, and when it reacts with the silica, it forms calcium silicate. So that calcium silicate is used for the concrete in the buildings and also for road surfacing. So these are the important features for the blast furnace for the extraction of the iron, and this is the summary of whole this extraction procedure. So in this picture you can see here we have key reactions for the extraction of the iron and the regions of the blast furnace where they take place. And a number of different reactions can take place in the blast furnace. The reaction that take place depend upon the position in the furnace and also the temperature that is required for that specific reaction. We have some regions of the furnace where the key reactions take place and the chemical reaction for these reactions. The iron that is produced in the blast furnace is only about 95% pure. 95% pure iron is produced. Pure iron is produced through the blast furnace. And the impurities that are mainly carbon, but they also include sulfur, silicon and phosphorus are also produced. Most of the iron that is there produced in the blast furnace is taken and purified further, and then we can turn into the various forms of the steel like stainless steel, mild steel we have, and steels are the alloy of iron that are used. Mostly stainless steels are also used for the cutlery because they are resistant to the corrosion, and steels are the alloy of iron, and we have a defined amount of our carbon that is present there. So steel is an alloy of iron and a defined amount of carbon is also present there. We can also add some other transition metals which are added depending upon the type of steel you want or you require. And if we add the chromium, if chromium is added with the nickel, chromium and nickel is added into the steel, then it forms a stainless steel, and that stainless steel is used for so many various purposes because it is resistant to the corrosion, right? So you can use it there also for the cutlery, right, because it is resistant to the corrosion. So this alloy is known as stainless steel. We have alloy is a mixture of metals that are present there. You can add metals, and also a non-metal can be there just for the requirement you want. So like the carbon, like carbon is added in the steel, defined amount of carbon is present in the steel with the iron. So you can add a mixture of metals just for the purpose of that, and we are adding the chromium and the nickel in the steel just to make the steel hard and resistant to the corrosion, to make it resistant to the corrosion, and that alloy is known as stainless steel, and stainless steel is used for making so many different cutlery items. So this picture you can see here, we have the first reaction that happens here is the carbon that reacts with the oxygen to form carbon dioxide. Blast of hot air will enter into the blast furnace from the bottom. So at the bottom the temperature is highest because hot air blast is added or is sent into the blast furnace from the bottom, that is hot. So a high temperature is present at the bottom of the blast furnace. So the carbon will react with the oxygen, or hot air reacts with the coke to form carbon dioxide. Carbon dioxide will move upward. When it moves upward, it will react with the carbon or coke that is present, more carbon or coke that is present, and forms carbon monoxide. This one is the second reaction, and that happens at 850 degrees Celsius. And then what will happen, the carbon monoxide reacts with the iron ore, that is the reduction process, and that occurs at 700 degrees Celsius. So this is the reduction of the iron ore in the presence of carbon monoxide. Then that forms the pure iron, that is of 95% pure iron is there. And we have also carbon dioxide gas. That carbon dioxide is again reused and recycled in this for the production of the carbon monoxide. Next, last step, we have to remove the impurities. The fourth one, limestone is used, calcium carbonate, that is heated, or we have a thermal decomposition process that decomposes to form quicklime or lime, CaO. That quicklime reacts with the sand to form the calcium silicate slag, and that impurity is collected from the bottom of the furnace. You can see here we have separate holes for the collection of the impurities like calcium silicate, and also you can also get the molten iron from the bottom of the blast furnace. So after that you can convert it into the solid one by cooling it. So this is how the extraction of the iron occurs from the ore in the blast furnace. So this is all about extraction of iron from the ore. Next we will talk about another metal, that is extraction of the aluminum from its ore. Aluminum. So we have the extraction of the aluminum from the ore. The main ore of the aluminum is bauxite. Bauxite is the main ore of the aluminum, and aluminum is extracted by the process of electrolysis. Why by the process of electrolysis? Aluminum cannot be reduced with the carbon because you can see here, this is the reactivity series. iron is present below the carbon, so iron can be reduced with the carbon because it is less reactive than the carbon, right? And if we talk about aluminum is present above the carbon, so we can't use carbon for the reduction of the aluminum because carbon is less reactive, aluminum is more reactive. The metals that are present above the carbon, they are more reactive, so we can't use the carbon for extracting those metals. But the metals that are present below the carbon, we can use the carbon reduction process by using the carbon for the extraction of the metal from its ore. So that's why we have to use the process that is electrolysis. As I already told you, the metals that are present above the carbon, you can use the process of electrolysis, and we have also done this extraction of aluminum in chapter number 6 electrochemistry, which is electrolysis, breakdown of the compound, molten or in aqueous solution by the use of electricity. So reduction with the carbon does not work for more reactive metals. The metals that are held in their compounds like oxides or chlorides by stronger bonds, they need a lot of energy to break them, and this energy is best supplied by the electricity. That's why we do the electrolysis process. Extracting the metals in this way is a three-stage process by the use of electrolysis. So the first stage, so if we extract the metals by the electrolysis process, there are three stages. The first one is mining of the ore from the earth crust. After the mining, you have a second stage, that is purification of the ore. You can purify it by using any technique. Purification or separation, you can use cyclone separator, you can use magnetic separation, you can use froth flotation process, you can use any for the purification of the ore. And the third stage, that is the most important, and that we'll do today, is the electrolysis of the molten ore. We can't do the electrolysis on the solid ore or solid metal, so you have to, because electricity cannot be passed through the solid one, because in the solid atoms are present at their regular shape and they have fixed structure, so that's why you have to convert it into the molten form. Electricity can be passed in the form of molten or in the form of liquid or in solution form. So the extraction of a metal by electrolysis, it's an expensive one, but by the reduction with the carbon is a cheap process. So for electrolysis, energy cost to keep the ore molten and to separate the ions can be very high, and many of these metals are extracted in regions where hydroelectric power from the dams is available. So we have aluminum plants that are known as smelters. That are the most important examples. They produce sufficient aluminum to make it the second most widely used metal in our after the iron. Although aluminum is most common metal found in the earth's crust, but it is too reactive with other elements to occur naturally as the free metal. So that's why we have the major ore of the aluminum, that is bauxite, and bauxite usually contains some iron oxide, which gives the ore its brown color. That's why the brown color of the aluminum is present there. So the bauxite is the major form of the aluminum ore, and it is the formula is Al2O3, that is aluminum oxide. And up to 25% of bauxite consists of the impurities, like 25% are the impurities like iron oxide in this. So we have 75% of aluminum will be extracted, like in the form of iron oxide. Impurities are there, and the iron oxide gives it a red brown color to the ore of the aluminum. So aluminum is extracted from the bauxite by the electrolysis process. The bauxite is converted to the aluminum oxide, by using sodium hydroxide. So we will do this in different stages. We have a specific process that is used for this one, for the electrolysis of aluminum, that is known as that is known as Hall-Héroult electrolytic method for extracting the aluminum, and that was invented independently by Charles Martin Hall and French scientist, that is Paul. So we have this process, and we will do this one for the electrolysis of the aluminium. We have some stages that are involved here, so we will discuss those stages one by one. So the first stage that is done here is bauxite. First we have the bauxite, that is the aluminum ore, and that bauxite is treated with sodium hydroxide. Bauxite plus we have sodium hydroxide. So this is the first stage in a refinery, just to obtain the pure aluminum oxide or to get the alumina or aluminum oxide. You can also call it as alumina or aluminum oxide. The alumina produced is shipped to the electrolysis plant. So this is the first one, and second one is the purified aluminum oxide or alumina. Al2O3 is then dissolved in the cryolite, plus we have a cryolite. Why we are adding this cryolite in this? This is another ore of the aluminum. So by dissolving the aluminum oxide in the cryolite, it will lower the melting point of the oxide and therefore working temperature of the cell. So cryolite thus provides a considerable saving in the energy cost. So when we add the aluminum in the cryolite, then the melting point of the aluminum oxide lowers down, so we have a saving in the energy cost. So this is the second step or second stage. And the third stage for this process is molten mixture of aluminum oxide and cryolite is electrolyzed in a cell fitted with the graphite electrodes. I will also share you here the third stage in the electrolytic cell for extracting aluminum. So this is electrolytic cell for the extraction of the aluminum. Molten aluminum mixture of aluminum oxide and cryolite is added here. You can see this one. This is the electrolytic cell and molten mixture is present there. So we have a graphite electrodes that are present there. This is the anode, the positive one is the anode, and the cathode, this is the negative one is the cathode, and cathode is the lining of the electrolytic cell. Just because of that, we are not adding any type of electrolyte in this, so we have just aluminum oxide and molten cryolite that are present there. And what will happen when we apply the electricity, or electricity is present, when we give it electricity, we have this process that runs continuously. Liquid aluminum is siphoned out and more alumina is added as necessary, and the voltage that is used here, that is quite low. You can see here just 5 volt is used, but the current flowing is very large, that is 200 kiloamperes. So a large amount of current is required. Large current flowing through the electrolyte produces a lot of heat, which keeps the mixture in the molten state. So when electricity or when current is moved through the electrode, it keeps the aluminum and the cryolite in the molten state because we require them in the molten state. So aluminum ions are attached to the cathode. Aluminum ions that are present there as positive ions, they are attracted towards the cathode because cathode has the negative charge, and the cathode is effectively the carbon lining of the cell. So aluminum is discharged as a liquid and sinks to the bottom, as you can see here. So aluminum will take the 3 electrons from the cathode, and now we have the liquid aluminum that is present at the bottom, and that aluminum is extracted by using a separate pipe, or you can see as here in our picture. So the reaction that happens here is aluminum Al plus 3 that will take 3 electrons from the cathode, and then it will form the aluminum as in the liquid state, but it's a pure metal or a stable one. So next, the oxide ions that are present there are attracted to the carbon anodes that represent graphite or carbon anodes, where they are discharged as the oxygen gases. So O2 negative will give the electrons, and it forms oxygen gas. So as to we are taking the 2, so 4 electrons will be given to the anode. So we have these two reactions separately at the cathode and at the anode. At the high temperature in the cell, the oxygen reacts with the carbon in the electrodes and also forming the carbon dioxide. Like carbon also reacts with the oxygen and also forms the carbon dioxide. Why this happens? Because of high temperature in the cell, the oxygen reacts with the carbon in the electrodes, forming the carbon dioxide. The carbon anodes slowly burn away and have to be replaced frequently. So this means that anodes need to be replaced regularly, but not the cathode. The cryolite is not used up by the electrolysis, and so alumina needs to be added to keep process running. So this process uses a great deal of energy, and it is also costly to replace the anodes. These costs emphasize why the recycling of aluminum is important, as it is much cheaper to recycle the metal than to manufacture it. The energy requirement for the recycling is about 5% of that is required or needed to manufacture the same amount of new aluminum metal. So this is the process through which you can extract the aluminum metal, and we have a Hell-Rod process through which you can extract the aluminum metal. And we have cryolite. Cryolite is basically the cryolite that is present there. Cryolite is just basically sodium, aluminum, and next we have fluoride. Sodium aluminum fluoride, an ore of aluminum that is used in this extraction of the aluminum just to lower the operating temperature of the electrolytic cell, and it is now also replaced by the synthetic sodium aluminum fluoride that is produced from the common mineral fluoride. So this is all about the extraction of the aluminum from the ore. Next we will talk about our second content of today's topic, that is the corrosion of metals, or the problem of corrosion, and also we'll discuss the rust prevention methods in this. So before moving towards the corrosion of metals, I will share with you a quite specific, or you can say that a technique, or just to remember, I figure out how to extract the metal from the ores, so you can refer the metal reactivity along with this one which I will share with you. Like we have a position in our reactivity series. This is just for your remembrance, position in reactivity series of different metals, and on the next you can write the method through which you can use or you can apply. So this one, if the metal is present under the hydrogen, if it is present under hydrogen, so that means that is less reactive than the hydrogen. So under the hydrogen, that means they exist as pure metals. Those metals exist as in the pure state, or you can say that as in the native state. Like you can see here, below the hydrogen we have antimony, bismuth, copper, mercury, silver, gold. So these metals exist in their native state, so you can't, or you don't have to do the extraction process on this one, as these are highly unreactive, so they occur as in the native state. Next one is, if the metal is present above the hydrogen, but it is present below carbon. So for that purpose, which method you have to use? We have a metal oxide that react with the carbon. So if the metal is present below the carbon, that means that metal is less reactive than the carbon, right? And carbon is more reactive, so you can use the reduction method by using the carbon. And if the metal is present above carbon, those are highly reactive metals and they are not reduced by the help of carbon, so you have to use the process that is electrolysis that we done for the aluminum. So this is just a hint for you to remember the which metal can be extracted by which method. So now next we have another topic, that is corrosion. First I will tell you the definition of this one. Corrosion is when metals slowly rust or wear away due to the chemical reactions with their surroundings. So when metals slowly rust, we can say, or they wear away due to the chemical reactions with the surroundings, and basically it is when the metals or the alloys are chemically attacked by the oxygen and the water in our environment. Moisture and water are required for the any metal to get the rust. So these are the two most important one. Without water, rusting or corrosion will not happen. So both of these are necessary for the corrosion or for the rusting to happen in any metal. If the metal is more reactive, the faster it will corrode. More reactive, then faster it will corrode, because it reacts very quickly, so it will react with the oxygen that is present in the air and also with the moisture, so faster it will corrode. That is why highly reactive metals like sodium and potassium are stored in oil, as they will instantly corrode when they are exposed to the air or the mixtures. Rust is also a form of corrosion that specially refers to the reddish brown. Rust is, you can say that the reddish brown color that is present there, or the flaky substance that forms on any metal when it corrodes. Flaky coating that develops on the iron or the steel surfaces when they react with the oxygen and the moisture in the presence of air. This is the rust, and rust usually consists of the hydrated. You can say that we have especially if the iron oxide or iron gets corrosion or iron is rusted, you call it as a rust. So if we have a substance that is that is made up of iron, so when iron corrodes, you call it as rusting, or that is known as now hydrated iron oxide, which is a reddish brown in the color. So the requirement for the rusting are water in the form of moisture or water itself and oxygen from the air. So these both of the above are required for the rusting. If either of them is not present, then the metal, iron or steel will not rust. Not that the rusting only occurs on the iron or the steel objects, there are so many other objects on which the rusting can happen. So this is about the corrosion and the rusting. So this is the problem that is present when a metal is attacked by the air, water or other surrounding substance, so it's said to be corrode. And when iron corrodes, the rust form is flakes and it does not form a single layer. The attack on the metal can continue over the time and the rusty flakes come off and holes can be formed in the iron sheets by the rusting process. Chromium is also another metal similar to the aluminum that is protected by the layer of oxide layer. Like iron is more you can say that iron gets corrosion so easily, but if we talk about aluminum, that is also useful as a construction material. It forms a protective layer. Like we have aluminum, and when oxygen, or you can say that the air and water combine together to form the corrosion, aluminum forms a oxide layer on the top, and then it will protect the underlying metal that is present there. So we have a protection layer of aluminum oxide that can made thicker by the electrolysis. So the metal surface protects and from the further attack. So that's why aluminum is resistant to the corrosion. Why aluminum is resistant to the corrosion? Just because of this oxide layer that is formed. So just like the aluminum, we have another metal, that is chromium. Chromium also forms oxide layer. If chromium is alloyed with the iron, a stainless steel is produced. It is too expensive to use a stainless steel for all the objects built out of the iron. So electroplating a layer of chromium on the steel is used to protect some objects from the rusting. So now we have rust prevention, or how can we prevent the rust. Now we'll see the procedures through which you can prevent the rust. Rusting is a problem because it weakens the structural integrity of the metal objects and also the structures. So to prevent the metals from rusting, it is important to stop either the oxygen or the moisture, both, from coming into the contact with the metal. All the methods involve isolating the metal from the surroundings by using a protective shield like paint, oil, plastic, etc. anything. So the first one in this is by painting. By painting a metal object. You know about the painting of the bicycles, cars. So applying a layer of thick paint to the metal surface forms a protective barrier. So when we apply it, it forms a protective barrier that helps us, or that helps the metal to not to get rust. So it forms a protective barrier that prevents for direct contact with the oxygen and the moisture, because a layer is present between the moisture and the metal. So that's why corrosion will not happen. Positive to this one is that the object will look also better. However, if the paint is scratched, the metal beneath it will start to rust, which will eventually spread under the paint. So next is greasing. So the second one you can use is greasing. Coating the metal with the grease or oil. You can say that we have a grease or oil. If we coat the metal with the grease or oil, a protective layer that repels the water and air, reducing the chances of rust formation. So greasing is often used for moving parts, for machinery, for equipments. You can use for the moving parts. We also give the oil to the moving parts of the battery, like bicycles, cars, all these things. So you have to provide the grease and the oil to those moving parts. Next we have the third one, that is with the plastic. So if we coat with the plastic, what will happen? The moisture and the water will not get to the metal. So the plastic can be used as a coating to isolate the metal from the corrosive elements, preventing the rust. So this is usually done in the pipes. So you can use it for the pipes, like the pipes which are made up of iron or made up of any metal which can corrode easily. So you can use this one. So these are the methods that you can use for the rust prevention. You can do either painting, greasing, by coating it with the plastic, or by using paint, oil, anything for the protection of the substance from the corrosion. Next we will talk about something that is galvanizing. So galvanizing is that when zinc is applied as a protective coating over the iron or steel surface, forming a physical barrier. So to do this, the object is dipped into a molten zinc and a thin layer of zinc is formed. So if iron or steel is protected by a layer of zinc, so what will happen here? We galvanize it. Zinc is more reactive than the iron or steel, and this layer also corrodes, but when the zinc layer corrodes, it transfers or it loses electrons to the iron, protecting it. So this protects the iron even if the zinc layer has been mostly scratched away. So we have a layer of zinc that is present on the top of the iron and the steel that will protect it from the further corrosion or the rusting process. So this is how the galvanizing is done. Next, we will also talk about this one, which is the sacrificial protection. We have the bars of zinc that are usually attached to the ships to prevent the iron from the rusting. This is done because zinc is more reactive than the iron. It is present above in the reactivity series, so that's why we what it is doing, it's a sacrificial protection, means zinc sacrificed itself just to protect the iron. So as long as some of the zinc stays in contact with the iron will be protected. When the zinc runs out, however, it must be replaced. So this is the same concept as the galvanization. So where when the zinc corrodes, it loses the electrons to the iron, like the equation. For example, we have zinc. If it is applied as a layer on the top of the iron or the steel, what will happen? Zinc sacrifices itself and it loses electrons to the iron, protecting it, as you can see here, as I show you here with the equation. So we have Zn plus 2 plus iron as a metal. So zinc protects the iron. So zinc is done here, or zinc is doing the role as a sacrificial protection. It sacrifices itself and protects the underlying metal that is present beneath it, like maybe the iron, that may be the steel, anything that is present there. So this is all about the chapter number 16, which is metal extraction and the corrosion. So we done with the extraction of the metals, and we also read about the extraction of the reactive metals by the electrolysis and some moderately reactive metals by the use of reduction with the carbon. And we are also done with the corrosion, metals corrosion, and also the prevention methods through which you can use that one just to do that. So this is all about chapter number 16. Hope you understand all this. If you have any question or any query, you can ask in the comment box. And if you like this content, then please subscribe our channel and share it with others also. We'll meet in the next video.